Hello everyone, welcome to Intelligent Healthcare and its applications. So this week we will move on to a very exciting part of the course, which including several applications of a neural network. And so we will begin with introduction to the neural network and its applications. So on our original agenda this week, we will talk about the convolutional neural network. But I think it's a good idea to talk about what is neural network and what is the original idea that about the simple neural network and how this idea evolves into the modern deep neural network. Okay. So the idea of neural network is not new. If you look at the literature, the identification of neural network can be traced back to 1877. At that time, there was a very famous neuroscientist called Raymond Caha. He is a very outstanding neurologist, and at that time there was no advanced imaging tools like computers, graph, or other digital imaging techniques. At that time, there was only microscopes. So if you want to look into human brain, then you have to make a slice of the brain tissue and put it onto glass and then look into the brain tissue through the microscope. So the Dr. Caha did a very good job at reproducing the tissue, the histology from what he had seen in the microscope. So this is one of the brain neurons he saw in the microscope, and so from this graph you immediately can see there are different types of neurons, and these neurons are connected to each other. So that was quite an intuitive idea about the neural network, and this is how we begin to know that there were lots of the neurons in our brain, and they are all connected to each other, and to make the information transfer and processing possible. Okay, so if we look at a single neuron, then we should be able to see this kind of the components. So every cell has a body. For a neuron, the cell body has several dendrites close to its body, but it has also a long axons extended from the body to a remote site. And at the terminal of the axon, there is axon terminals which connect to the other parts of the neuron. So the receiving parts of the neuron we call these dendrites, and the output or efferent, the component of the neuron we call the axon terminals. So this is the way that each neuron connected to each other, and so it's very important to know that how neuron works and why the neuron can have several inputs and also several outputs. Okay, so in the left figure, so you can see several neurons and the types of the connections between axon terminals and dendrites or neuron bodies. So you can see that actually each neurons can receive inputs from several axon terminals, or you can call these presynaptic inputs, and these inputs can be both excitatory or inhibitory. So the neuron itself is kind of the perceptron. It receive the signals from several outputs from several neurons, and also the neuron itself needs to process this information and to determine that if this signal should be transmitted through the axon. So you need to determine that if these inputs are sufficient enough to fire the electrical pulse and to transmit the signal to the next neurons. So that is the basics of the neural network. And if you look into the further detail into the axon terminals, then you will see that there is a very small space. We call that the synaptic cleft. In the upper parts, which is axon terminals, or you can call this a presynaptic region, and also the other side, which is the pre-post synaptic areas. And in this small space, the neuron relies on the neurotransmitters to transmit the electrical signals and convert it to neurotransmitter released into the synaptic cleft and received by the receptors on the postsynaptic membrane and convert this chemical signal back to the electrical signal. So this is an amazing combination of the chemical and the electrical signals, and there are many mechanisms to balance the information processing. So any kind of imbalance in neurotransmitter will result in certain neuropsychiatric disorders. So that is the beauty of our human brain, but it also gives us a very good intuition that how can we learn or build a mathematical model from this kind of a neural network, and to do a very amazing analytical job. So we can think that neuron is an information processor. So as I said, if we simplify the biological mechanism I just showed you in the previous few slides, then we can make this a diagram which is very simple. It has 3 inputs. So you can see that these inputs are outputs from the other neurons. So we have 3 inputs, which is x1, x2, and x3, and each carries a different input values. And as I said, this input value is actually the output from the other neurons. But here I just show the one neuron, so it received the 3 inputs. And the neuron itself must process this information and give a certain output. And this output will be served another input into other neurons. So that makes the whole neural network work. So let's think it in a very simple way. So each input value we can just give some weights to these values. So the weights means that for a certain value, for example, if we give the input value as a 10, then another value could be the 2 or 5. However, these values may contribute differently to the neuron or the information processor. So for example, the input value 1 may be multiplied by the weighting factor 1, and also the input value 2 can be weighted by the weighting factor 2, and similarly input value 3 can be weighted by the weighting factor 3. And in that way, we can sum up these weighted input values. And what does that mean? Because as in the previous slides, you see that each neuron can receive inputs from different neurons, and these different inputs can include excitatory and also inhibitory inputs. So for example, if we give the positive weighting factor here, then you can see that this may mimic the excitatory inputs. If we put the negative values in these weighting factors, then this may mimic the inhibitory inputs. Means that if you have always positive input value, but if you weight it by the negative weighting factors, then this the summation of all these weighting procedure will have a summation of the excitatory and inhibitory data. So the output Y here can be regarded as the summation of these weighted values. So that is what I say about the neuron as an information processor. But also you can see that if the output is the summation of the weighted input values, this equation is very similar to the regression model we introduced in the previous courses. And actually that is true, because if you just put a single neuron, build a single neuron model, it almost acts like a regression model. So that is, however, if you can connect different neurons together, then you can imagine that these multiple neurons can process much more complex information than the regression models. So that is the improvements of the advantage of the neural network models compared to the linear regression. Okay, so in the biological neural network, we also observe a very important characteristics, which is the all or none rules about the neural activations. So despite that a neuron can receive many inputs, there's only all or none patterns in the output. So the neuron must decide that whether or these inputs should fire the output signal or not. So in that way, we cannot just designate Y as the summation of the weighted input values, but we need to give a function to process these weighted input values to determine the output. So this function is very important, because the function is just sometimes just like a black box, and so it just process information here, but can also give a very simple output like 0 or 1, or between any value between 0 or 1, means that it just determine all or none rules. Okay, so these functions can be realized by, for example, the threshold functions. So here you have an x-axis, which is the representations of the summation of the weighted input, and the vertical axis represents the output. So in the previous slide here, we just sum up all weighted input values and to directly output that value as a Y. But here we need to use a function to determine the outcome of these weighted input values. And this threshold function defines that if these weighted input values is larger than 0, then output should be 1. If these weighted input values are below the zero, then the output should be 0. So that is very intuitive, because if you think that these inputs include both excitatory and inhibitory influence, so these influence or input value can be summed up together, and if the summation of these excitatory and inhibitory inputs are above 0, means that these are still the overall the information is still the excitatory. Then we will give the output as 1, means that the neuron should fire the electrical signal to the axon terminal, and to make sure that the signal will be transmitted to the next neuron. However, if the summation of the weighted input value is below 0, means that the inhibitory influence is outweighed the excitatory influence, then the neuron should do nothing. So there's the output should be 0. Okay, so this threshold function is very convenient, but it has some limitations. So we in reality, we prefer these kind of the sigmoid the functions, which output a value between 0 and 1. But in the activation functions, the threshold function is very useful. When we do the output, we want a function that gives a probability-like values, so which is between 0 and 1. So if we have a kind of the input just very close to 0, and you have a kind of probability close to 0. And in the contrast, we can have if the model thinks that this is close to 1, then this sigmoid function will give you a probability close to 1. And also, in some cases, we may need an output just between -1 and 1. Then in that case, you can use hyperbolic tangent. So that is only we use different kind of mathematical equation to define the activation function of the neuron. So these 3 slides actually tell us that different types of activations about the neuron. So this is about the threshold functions. When the input is above a certain threshold, then the neuron will fire an output. And in this case, then the output is somehow dependent on the value of the inputs, and also the hyperbolic tangent. Okay, so don't worry about how to use these functions, because I just want to give you a flavor and illustration how we use mathematical function to simulate a neuron. And for the neural network, I think one of the good strong motivation to do the neural network is that we want to simulate a human vision system. So human vision system is a very complex but also elegant an organ that enable us to see something. So it combines the physical and chemical and also electrical mechanisms to transmit the data or the information into our brain. So initially these inputs are light, and the light can penetrate through the corneal lens and to the crystal body, and to finally to be received by the retina, which contains many receptors can respond to the light stimulations. So these receptors will convert light signals to electrical pulse through the optical nerve, and this impulse will connect through a very complex neural network, and in our brain. So this is the human vision system contains a very sophisticated neural network, and the main processors of this visual information is in our back of the brain, which called the occipital region of our brain. So the visual cortex is in our occipital brain, and it's very, very important because it contains a large part of the brain to process this visual information. And if you look into the cortical layers of this visual cortex, you can see a very complex combination of the different types of neurons, and they are all connected to each other in a certain manner. So not only they connect to on the vertical way, but there's also neurons that can communicate in a horizontal fashions. So this is really the inspiration to mathematicians to develop mathematical equations and neural network to simulate these biological phenomenon. Okay, so if you have just from previous few slides, you should have some insights about the biological neural network. So here, we can combine several single neurons into a simple neural network. So in this simple neural network, we still have several inputs. So for example, here we have 3 inputs, maybe the m inputs from the x1, x2 to the xn. So these input values will connect to each neurons, or we call these perceptrons. So each neurons will receive inputs from each source, and these neurons will all connected to the one output neurons. Then these output neurons will give an output values, so to give us the answer or the result of the information processing from these input signals. So you can see that for the multiple neurons, we have more connections. And the challenge is that how do we determine this weighted input and to give a reasonable or corresponding output here. Okay, so from this graph, you can see there's an input layer. There's no question, but the important part is that we have a hidden layer containing several different neurons, and they are all connected to the one output neurons, which give us output of this information. Okay, so the simple neural network contains the input layer, hidden layer, and output layer. So there's only one hidden layer here, but you can specify as many neurons as possible, but there's also some disadvantage if you just assign too many neurons here. Okay, so for this hidden layer, then we commonly choose the threshold functions as the activation function. Means that only when these inputs are above a certain thresholds, then the neurons will fire up an output to the output neurons. So that threshold function is very important, so it can determine if that input information can be transmitted to the output. And for the output neurons, we often use the sigmoid functions because we want a probability to represent the potential chance that how this information can be corresponding to a certain classifications. So we use different types of the functions to process this information. And the question is that if we have a weighted input value here, and we also defined a processed information here as a function, then the output values may have a certain difference with comparing to the actual values. So the difference between the output values and actual values can be defined as an error. So usually we define the error as a squared, the half of the square. Okay, so this error can help us to determine if this model or this neural network is good or not. So although this is a simple neurons, not simple neural network, but you can see that if we connect different neurons together, then we can also define the difference between the output values or predicted values and actual values. So that error can help us to determine how this information should go through these neurons. Okay, so how do neural network learn? So it learns by the non-knowledge. So for any neural network, if you want to do the classification or regression, then you need to know the actual output of this information. For example, if you want to predict, for example, that the home price, okay, so every real estate property has its own price, and that price is sometimes determined by, for example, the age of the house and also the type of the house. For example, the condo is usually cheaper than a single house, but also by the locations. If the location is very good, the price is higher, and also if the house is the new one, the price is usually higher than the old one. But that is a very complex factors influencing these inputs. So there's a complex weighting function here to process different kind of information, like the age of the house, the type of the house, the location of the house, etc. So if we want to give a very useful function to predict the home price from these informations, then we need to measure the error between the predicted home price and the actual home price. So if you have lots of the home price data, then you can learn from this data to define these weighting values. So these errors can be propagated back to the model to adjust these weighting factors to make sure these predict values is very, very close to the actual value. So that is the original idea about the neural network, that we can evaluate the difference between the predicted value and actual value, and using this error to propagate it back to the model to adjust the weighting factors here. So that is the way neural network learn how to model the data. And there may be some problems here, because if you we always want to minimize the error. So in that case, we want to find the optimal weighting factors to minimize the errors of the predicted values. Means that we want to minimize the difference between the output and actual value. However, that process is not a very straightforward way, because how do you determine the error is the smallest one is the question. So for example, if you can test different parameters, and probably you will find, I think that, okay, this is the local minimum. So if you have suppose that the vertical axis is the error, and the horizontal axis is the parameters of the weighting factors. Then in this case, you might think that, okay, this is a good point because in here we already find the optimal, the minimum errors. So because at this point, this is a local minimum of the errors, and if you put parameters smaller or larger than this one, the error will increase. However, sometimes we don't have a sufficient resource to test every possible parameters. So we cannot always foresee that there is a even smaller error here, so can make our model the best. So that is a challenge in the neural network models, and actually this is the one of the limitation that prevents the neural network model prevail from other models. So in the early time, there was no powerful computers. There's only like very simple computers and with limited power to calculate a limited number of calculations. So if you compare the neural network with the linear regression, you will find that the neural network requires lots of the computations. Then you really need a good computer to do the neural network modeling. So in this gradient descent example, you see that if we don't have the sufficient computation power, or if we don't have a smart algorithm to find the optimal solution, then you will miss these optimal regions, and you think that the model can only perform at this certain degree. So so that's why in the training of a neural network model, we always need several iterations to test the different parameters and to find the optimal solutions. So that's what takes lots of time to complete these iterations. And the problem is that we always do not have a clear idea what the gradient descent looks like. So one of the solutions is the stochastic gradient descent. So we just randomly test the different parameters and hopes that one of the trial can give us the best result. So that is one of the possible solutions to the gradient descent problems. But anyway, so these slides just give you a very intuitive insights that how simple neural network work. So if you have the inputs, then you just pass this information through the hidden neurons, and the information will be processed and connected to the output neurons to give the classification of the input. So we will hope that this input, for example, the dog images, will also give the output as the dog. And if you have images of the cat, you also expect that the output will be the cat. And for the deep neural network, then it just means that we have more than one layer of the hidden neurons. So this is a simple, kind of the very premature form of the deep neural network. So you have 2 layers of hidden neurons. So you can see that there are lots of connections compared to the simple neural network. And that is also a problem because, as I said, in the early time, although mathematician already gives a very exciting theory about the deep neural network, but there was no computer can do such very complex computations. So, for example, if you have many variables, and you can also give as the output, then as I said, you also need to evaluate this output to calculate the difference between the actual classifications and the predicted classifications, and you propagate that errors back to the model. And in the case of deep neural network, because you have too many weighting factors to be adjusted, so you really need a good theory or good algorithm to do this kind of job. And that is one of the breakthrough in recent 10 years, because the mathematician already found a very good solutions that can help us to determine these weighting factors in the limit time of the period, in the limit period of time. So the comparison between the simple and the deep neural network is these things. So in the simple neural networks, you have only one layers. And in the deep neural network, you have the multiple hidden layers. Okay? So one of the famous example about the deep neural network or simple neural network is the recognition of the handwritten digit. So we know that everyone has a different styles of writing digit numbers. So for example, if you have ever chance to go to United States or Europe, you will find that the way of writing Arabic numbers is very different. Okay, so that's why we need a very efficient algorithm to recognize these numbers. And this is very useful in financial areas because there are lots of the receipt and lots of the handwritten number informations. We need to digitize these informations, but without any errors. Okay, so I will illustrate how we do this in the deep neural network. But for now, I want to show you how to train a simple neural network. But before that, I want to just show you the history of the evolution of the deep neural network. So you can see that about 10 years ago, there is only shallow network. And in 2012, there was a big breakthrough that there is a LexNet. So these figures show you the benchmark of the neural network in the imaging classification challenge. And this number represent the errors. So you can see that 10 years ago, the errors is still high because there's a 28.2% of images were misclassified. But this breakthrough happens in 2012 that is using a deep neural networks, which contains 8 layers of hidden neurons, can reduce the errors from 25.8 to the 16.4. And from that time point, we developed more and more complex neural networks, including more layers. For example, in 2014, the VGG models contains 19 layers, and the GoogleNet contains 22 layers, and the ResNet contains 152 layers. And if you look at the more recent models, and there are more than 300 layers in certain models. So you can see that once we incorporate more layers, then we can have improved accuracy or reduce the error in a significant rate. However, because you have so many hidden layers, you need lots of computation power to do this model training. So that's why we need a very sophisticated hardware like GPU, graph processing units, to do this lots of the computations. And this figure also show you the evolution of this deep neural network. So the accuracy the benchmark can be from the AlexNet to the latest Inception V4 has gone from the 55 to the more than 80%. But in the right, it also show you that although you have a very high accuracy in some models, at the same time, you also need lots of the computation powers and shown on the horizontal axis. So that is why we, in most of the time, we need lots of the computing powers to do very complex deep neural network training. Okay, so back to the simple workshop in this part of the course. Then I will show you how to do the simple neural network. And I need to admit that the Matlab itself is not a very good platform for the neural network training. However, it does provide a very good functionality about the neural network fittings. So if you look into the Matlab documentations, and there are many examples tell you how to do the simple neural network training, and there's even an app to do the neural network fittings and regressions. But I think for the simplification, for the teaching purpose, I just want to show this simple neural network toolbox you can download from the internet. So if you type the simple neural network in the browsers, you will find this page. I also provide the link here, so you can link to this the web page. So the Matlab has a mechanism called the file exchange. So anyone has the ability to write the codes, then you can contribute your codes on this file exchange platform. So this toolbox was created by the Dr. Zahid Toyan. I cannot spell this name, but it has a very good functionality. So you can see that you can just use a kind of universal mechanism. You can just make a model by learn NN and give using the input and output, and you also can do the prediction from the trained models. So it's very similar to what we have done in the regression course. So I will show you how to use this toolbox to do the simple neural network. So the first thing, you need to download the zip files, and please unzip the file and rename the folders. I will show you how to do this and add the path in the Matlab. Okay, so here I want to show you how to do this in a Windows platform, but it's very similar to do the same thing in the Mac OS platform. So once you have downloaded these zip files, you can place anywhere in the folder you want. But in my case, I just put into the create a folder called the program source, Matlab, and machine learning. I just put this toolbox into the machine learning folders. So I make sure that everything of the machine learning codes will be placed together. Okay, so in these folders, you just try to unzip these zip files, and for example, I just unzip to these original directories. So in this case, I just click on this one and rename is a simple NN. So it's to be to simplify the folder name. Okay, so next thing is that you need to specify the location of this toolbox in the Matlab. So the Matlab will know how to find this toolbox, where to find the toolbox. So in the Matlab, you can see that in the home panels, there's a set path button here. So just click on this set path. then here you can see there are lots of the search paths to define the location of these toolbox. And because this is a customized toolbox, you need to add with subfolders that just goes to the location of your simple NN toolbox. Here in my case is under the machine learning and simple NN. So just click on this, you will see that there are 3 folders being added to the search path, including the root folder simple NN, and also the subfolders including data and lib library. So just click on the save and close, so the Matlab will know how to find your toolbox here. Okay, so once you have downloaded and installed this toolbox, then we can do something with the data. So remember, in a couple of weeks ago that I showed you how to use the logistic regression to classify the primary insomnia and patients with the obstructive sleep apnea just based on the questionnaire data. So this PSQI data, at that time we used linear regression to explore this question, but here then we can revisit this data by using a simple neural network. So if you still have the data, then you can work on this data with a simple neural network. So just try to recap the data pre-processing procedure I already showed you in the previous course. So the first thing you need to do is to input the data by the read table functions. So the original data is stored in an Excel file, so you can use the read table function to input the data into the Matlab. And the next thing is that you want to define the predictors and response. So in this case, we use the predictors as the PSQI data from the second columns to the last column, okay? And the response is this diagnosis. But you have to categorize this response and to make this a double format. So I just show the codes here. Is the first line is convert the table format to the data format to the numerical format, and the second line just convert the categorical data to the numerical format. So the next thing is that try to train the simple neural network models, and in this toolbox you just simply use the predictors and response as the input parameters and just learn NN functions to make a model. So we can, if you execute this line in the Matlab, you will see there are many iterations, but it should be very fast to do the model training. Then the next thing is that you need to predict the output of these classifications based on our predictors. So the predict NN is using your model to predict to generate the output from these predictors as a P. So the P will be also 1 or 2. So remember that in that logistic regression course, we use the confusion math functions to generate a confusion matrix. So using these confusion math functions, we can compare the results of the predictions, which is stored in the P, and also the actual response here. So we can visualize this confusion matrix using the confusion chart functions here. So immediately you can see that actually the results of the simple neural network is very good. It can have 92 cases in the true correct classification as a 1, and also 91 cases of the 2 is correctly classified. So if you want to calculate the accuracy, is the summation of the 92 and 91 and divided by the 200. So So here we have the accuracy above 90%. Okay, so which is a very good one. It's a 91.5% accuracy. So comparing to the logistic regressions, you can see that the simple neural network is doing very well. It achieved about 91.5% accuracy. And in the logistic regression, I put the logistic here, is also a kind of linear regression. And the result is the accuracy is only about 78% of accuracy. So you can see that there's still an advantage of a simple neural network as long as you have a very good correct assignment of the hidden number of neurons in the hidden layers, and then you can have a more accurate model than the conventional statistical model. Okay, so we will stop here, and in the next course I will show you how to incorporate some new ideas into the neural network to form a so-called convolutional neural network. Okay, so see you in the next course, and bye-bye.